Hey guys, so we're gonna be starting now, and if you haven't gone to a breakout room, like had one or this one to come to, and we'll be having two sessions. So if you're interested in both of them, you'll be able to go to both of them at once. Let me try this mic. Oh, I think this mic is better. Okay. So I guess we can get started now. So this room is where I'll be giving a quick introduction to like robot vision and how you can use the camera and the webcam to be able to detect things in the robot field to have to be able to better control the robot in more intelligent ways. Okay, so let's dive right in. Okay, so on the agenda today, we're basically only going to be talking about robot vision, but we're going to have several portions of this to be talking about. So one of these is going to be TensorFlow, which is basically a machine learning or slash artificial intelligence tool that you can use to be able to recognize objects. And this is especially useful when you have a more distinct shape or coloring of an object that you want to be looking at. So usually with TensorFlow, every year the FTC provides a pre-trained model for you to be able to use. And this year, the model that they provided for us was to detect like the signal at the beginning of autonomous. And like just those three sides, they gave you that model already so that you are able to directly use it and have it like tell you which parking space to go in. And this was like in a sample class within the FTC library. The second way is more of like a conceptual method. And the individual implementation for each team, if you want to like sort of incorporate this into your code, the individual implementation will be slightly different depending on like your other code and how you want to incorporate it together. And yeah, so this is just more of like a original algorithm that each team might want to write themselves. It's just like the conceptual overview of what it is in case you want to implement it yourself. And the last section we're going to go through is going to be for other tools, such as like OpenCV. I'll give like a quick overview of what it is. I won't dive super deep, but in case you want to check it out and see if you can work better with OpenCV instead of some of the other earlier options, you can start to check that out a little bit. Any questions before we begin? No? Okay. So let's first go into TensorFlow, and this is more supported with the Vuforia engine. So yeah, let's just go into that. So first, let's try to understand how TensorFlow works, not like the machine learning itself, but more like how we can leverage using this this library given to us already to be able to use it to detect things. And so we're going to use something called the TensorFlow object detector, which is already already a class that they pre-made for you in the FTC library and is ready to use already. So if you want to be able to find where like an example class would be for using this object detector, you can look under FTC robot controller, which contains all of like the example codes and classes for you to look at. Under Java org.firstinspires.ftc.robot controller, and under external samples, you're going to find a class called concept TensorFlow object detection, which is going to like give you a general overview of how to like load in the camera, how to load it in Vuforia, and then how to use like the model itself to be able to detect like objects. And what it returns, it will also give like an example of how you can like loop through the data and basically leverage that to find where the parking space is, for example, this year. And the main like thing you're going to use is called TensorFlow light models. So TensorFlow has TensorFlow is basically just like the machine learning part, but the individual detection of objects are actually going to be held inside the models. So TensorFlow light models are basically trained like programs that store data on what objects basically look like. So TensorFlow is able to use those to be able to like accurately tell you, oh, this is a car or that's a truck. Each of that takes a lot of training data, and all of that culminates in like the TensorFlow light models. Okay, so let's see what the data it gives you is. So there's a class called recognitions within TensorFlow, and a recognition is basically one of the objects that the TensorFlow model is able to look at, or the TensorFlow recognizes, right? That's why it's called a recognition. And so this is essentially a data class that returns a bunch of data about the objects that are within the screen, right? Within the camera. So a lot of the important information about these recognitions come in the label, the bounds, and the confidence. And I'll go into a little bit more detail right now. So labels are essentially the type of the object that you're looking at. So if you see that there's a bunch of ducks on the screen, right? The labels on the bottom of the bounding box. And in this case, the label is duck. So this is basically telling you I'm looking at a duck. If you're looking at something else, like a car, then the label would be a car under that. And you would be able to get that information back from the variable passed back by the TensorFlow model. So that's one of the most important things, because you got to know what you're looking at in order to know how to work with it. In this year's challenge, label is basically enough to recognize where the signal is, right? Because you're going to have 3 sides of the signal, and each side has like a different image on it, and TensorFlow will return a different label for each side because the image it's looking at is different each time. And that label is enough to determine which parking spot you need to park in, because like side 1 means parking spot A, side 2 means parking spot B, and side 3 means parking spot C. So that in some cases, label is already enough to tell you. Label already gives you enough information in some cases. Another very important attribute to recognitions is the bounds. So essentially what the bounds are is it tells you where the object is within the image. And these bounds like basically tell you, is my object like to the left, to the right, or is it like where is it within the context of the frame of the image, right? So these bounds like help a lot when you want to determine more information about the object, like where it is. Like say you want to be able to drive to an object. If you want to drive to an object, then not only do you not want to know what object you're looking at, you also want to know where the object is within the image, so you can do some extra calculations to actually pinpoint the actual location, so you're finally able to drive there. So bounds are also very important in some cases, depending on what you want to do with the information you find. The third important attribute is the confidence level, and this exists because TensorFlow isn't perfect, so it's never 100% sure that this is a duck. And there's always some percentage of like certainty it has with these objects. Now, if you set the confidence level to 0, like return all objects that you are more than 0% sure are that object, you're going to get a ton of objects all over the screen because it somewhat resembles a duck, say, and then you're going to get a ton of ducks. But if you set it to say you'll have to be 80% certain before returning that this is indeed a duck, right? Then you get a lot less ducks on the image on the screen, and the boxes that you're going to get around the objects, those are going to be much closer to what you want to see. And in this case, you can see I have 2 ducks on the screen, and the numbers on the bottom right are the confidence levels. And so that's going to be 96% confident is out of like 1. So 0.96 is 96%. So that represents that the model is 96% sure that this is indeed a duck. And the one on the right is only 89% certain for a variety of reasons. It could include like lighting, angle, distance, a bunch of stuff like that. So this also helps sometimes if you are expecting to see only one object, but it returns 2 objects. The one like trick that you can use is to take the object with the highest confidence level. In this case, I would take the duck on the left because the model is more certain that that is indeed the one I'm looking for. So that's also one thing you can leverage to try to get the best possible like result from this model. Any questions about recognitions, or do you have any other questions about other attributes that you might be able to use? Yeah? That's a great question. So we're gonna talk about creating your own models later on. For like a lot of the game, you're able to use FTC's model, but like this year, there's like an extra 10 points for parking if you use your own images instead of their images. In that case, you would probably want to train your own model, right? Because you want the extra 10 points, and it's also a good experience to be able to know how to train a TensorFlow model. Okay. Any other questions? Okay. In that case, I guess I'll move on. So here are some examples from past years of like the provided models. So 2 years ago, the images are swapped. Sorry about that. But 2 years ago, well, actually, sorry, they're actually not swapped. I lied. So 2 years ago, we had Ultimate Goal, which had was a game with rings where you had to shoot rings out of your robot, and there was a provided TensorFlow Lite model that was able to detect how many like rings were in the stack, because the parking 2 years ago was determined by the number of rings in the stack. It could either have 0 rings in the stack, which is just like an empty stack. That's like the first parking option. Or there's 1 ring in the stack, like a short stack. That's another parking option. Or there's 4. So here in the image, you can see 2 examples, 2 images, one with 1 ring in the stack and one with 4 rings in the stack. It's hard to see, but on the bottom left of each image, the first one says single and the second one says quad. So that's like the provided TensorFlow model working there and telling you how many rings are in the stack. So on the right side, there's quad. So that means there's 4 rings in the stack. On the left side, it says single. So that's 1 ring in the stack. So that basically, the label itself there is basically enough to tell you where you want to park. So that's very powerful in terms of like parking. So that was enough 2 years ago. You didn't have to do anything else. There wasn't any extra parking points for anything else. So like you said, if we had to train our own, 2 years ago, you wouldn't have to train your own because that would be enough for parking. Last year, they provided a TensorFlow model to detect a few more things. So BCDM was like their name, and that means like ball, cube, duck, and markers. So last year, the game was played with yellow cubes and white balls and yellow ducks, as well as tape markers, which if I can show, oh, I don't have a picture of it, but it was basically like square tape markers on the ground. And some teams, I guess you would be able to use the position of those tape markers to determine which one was covered. Because there was 3 tape markers on the ground 2 years ago, and one of them was covered by an object that your team creates. And in order to park, you would have to determine which marker was covered. And using this TensorFlow model might be able to help you determine which ones are covered and which ones are not. And that's also where the position, the bounds from the previous slides, the second point here, that's where those come in action, because those tell you which markers are covered, right? Because the one in the middle, the one on the left, or the one on the right. Those will tell you that information, and that determines which parking spot it is. So last year, it wouldn't have been just with the label. You would also have to have the bounds if you're using TensorFlow. Okay. So and with the balls and cubes and ducks, one other like application of that would be if you wanted to detect balls and cubes where they were to automatically pick them up. That would be a valid way to start trying to automatically seek out balls and cubes. Granted, it's not like the most accurate or precise way of like achieving that kind of vision, but it is one way that you could try and play around with. Okay, so now let's move on to creating our own custom TensorFlow models and how we can do that. So this season, actually, FTC actually released a very nice new like website that allows you to easily train your TensorFlow models for FTC specifically. And the reason they did this was because training models for FTC specifically is actually not very easy, because you need a specific type of TensorFlow model, TensorFlow Lite, and not only that, the format of that model has to be compatible with the FTC SDK, and a lot of the time it's not. So last season, I tried training one like in a traditional way, like training a TensorFlow model, like following a TensorFlow model training tutorial, like just a general one, and it turned out that that didn't work for FTC because it just wasn't compatible with their thing. But now with the FTC machine learning toolchain website, that automatically creates you input like data, and then that automatically creates a model that's still compatible with the FTC SDK, and that way you're gonna be able to use your own TensorFlow models. And this season we actually leveraged this tool to be able to create our own TensorFlow model for the custom signal. So it actually works decently well. Another possibility you could use to have a custom model, not really created by yourself, but the internet is a great resource, and there's already a lot of pre-trained models on the internet that are not the default one given by FTC. And I know some teams who have pulled out some models from the internet and just use those images as their signal images, right? But the problem with those are they might not be trained very well. Maybe they don't really work well on like on the field, like on the FTC field. So I would be careful if you're gonna pick those. Maybe you can find a good one, but yeah, that's still an option though. Like it's still compatible, it still works. Yeah. And I think we can check out what the FTC machine learning toolchain website looks like. So the first link kind of takes you to like the documentation part on how you can do stuff, and the second link is the actual tool. So we can go to the second link right now. Let's see if I can make this page just a little bit bigger. Okay, so this is what the home page looks like of the first Tech Challenge machine learning toolchain. And as you can see, we have several designs here already. So we tried out several different designs here. The first one was with some random animals. The second one was with some fruit, and the third one was with like robotics related logos. And yeah. So if we look at like, if we click into one of these, you can kind of see how the training process works. So what you're gonna do is you're gonna take, instead of taking a lot of images, which is what you would usually do, like of the object, this makes it a little bit easier because it allows you to take one continuous video of the object, and what you can do is you can like change the lighting, you can change the angles during that video, and that basically produces a wide range of images that allows you to train really well, right? Because ideally you don't want the same image over and over again, because that doesn't really teach it anything new. You want it to be able to recognize the object from different angles and different lightings. So in this case, you can see that the lighting is changing, it's getting darker, and then we change the angle a little bit, and yeah, and we change the angle again. So basically it changes this angle, and what you can do after that is you select the object you want to keep it focused on and tell it that's the object you want. And you can see it says tracking with OpenCV over here. OpenCV, which I'll talk about later a little bit, that will actually track the object once you select it with like a box. Like you can select a box here and then name it something. But I don't want to do that right now. So yeah, so you basically draw a box around the object that you want it to learn and then name it the label. And then that label will become in use earlier when later when it returns recognitions. So yeah, this tracking with OpenCV basically keeps the bounding box around the object even if you move it around. So that's like a different vision that's helping you train your own vision. So that's pretty cool. And there's also like different algorithms of OpenCV that you can use to keep it tracking, but I don't think it matters a whole lot. So yeah. So this video, like this video that you take and upload and then select the object on is basically all of the data you need to train. I do want to note, however, there's like a time limit for each team. I don't know if it's all season or just for each season or just like forever, but this is still like an experimental model, I guess. And the computation is not free for FTC. So obviously they don't want you like training all the time and like using up all the resources, right? Because that takes a lot of money and a lot of the resources. So each team, it's very generous, but I do want to note, don't like randomly keep training models over and over and over again, because eventually you're gonna run out. But for like normal use, it's very generous. So yeah. Okay, does anyone have any questions about custom models and how you can train them right now? Okay, I guess we can move on then. So yeah, that's about it about TensorFlow models. The default ones, the custom ones, you can either make your own on the new tool that they provide, or you can find some on the internet. There's probably a lot out there that are for free, and you can try those out as well. Okay, does anyone have any questions about not just models, just TensorFlow in general, how you can use it, where you can find the sample code and whatever? Yeah? I believe it's a lot easier to use it in Java, or I think Kotlin works too, because the two languages are compatible. I believe you're asking if you can use it on like the block kind of thing interface. I'm not sure about that because I haven't used that, but I would assume Java would be a lot easier to use. Yeah. But there is like the sample program, and you can kind of follow through that, and that's like a working example of TensorFlow. Like you're gonna be able to see the objects recognitions and stuff. So maybe you can use that as an example if you want, and that should work out pretty well. Yeah. Any other questions about TensorFlow as a whole? All right. If not, I guess we can move on to the next subject. Okay. Before we move on, actually, why wouldn't we use TensorFlow? And there's a variety of reasons. The first is once in like a structured setting, it's pretty good for detecting the object, but like the FTC field is really big, so distance is a huge factor. If it's like 1 foot to or like 1 or 2 tiles away, it might work. But once it gets further and further away, there's a lot more distractions. There's a lot more other game elements. There's other robots there. The robots could have like colors that confuse the TensorFlow model. There's just a lot of factors once you move further away from the object that might allow TensorFlow to make a lot more errors. That's why usually it's best to use it in like the before autonomous situation, because you know everything's right there. Everything's going to be like that every time. So it's going to work out a lot better in those situations. But like during gameplay, during matches, it's going to be a lot more like varied, and you just don't know what the model is going to think of other robots, maybe even like refs outside or other spectators, because that color will confuse a lot of stuff. Another thing is lighting, because like the field lightings in each venue of competition are completely different. And although the model does try to account for like different lightings, you would probably want to like put in different lighting settings, right, while you're training. But lighting can still affect it a lot, especially with like shadows and stuff. If the light's from a different angle, it's going to be harder for it to see. The third thing is inaccuracy. TensorFlow does have some level of inaccuracy, especially with like training your own or even their trained ones, because a lot of like machine learning or AI like stuff out there, they have like tons and tons of data to train them to make them just like 90 or 95% or a little bit more good. They have like tens of thousands of images, and that's just not possible on like an FTC level, because you don't have access to that amount of varied data that you might have. This could be one reason that online models are good, but it's hard to find good ones online as well. So yeah, so the inaccuracy kind of comes from the limitations you have while training the model. And the fourth one is it's very inflexible. The information they have that they return to you is the only information you get. You can't go through the image. You can't do anything else. Again, for like determining where you park on the field, that's fine because you don't really need a huge amount of flexibility in order to make it work. But if you're going to detect stuff like and then go to it, for example, like I want to be able to adjust my arm based off of where objects are on the field, like TensorFlow wouldn't be very easy to incorporate into your program. Yeah, so the 4 reasons that I would kind of say stay away from TensorFlow at some times would be because of distance, lighting, inaccuracy, and the inflexibility of TensorFlow. So what are some other alternatives to TensorFlow? And I'm just going to be talking about a few of them right now. So the first one is what I like to call image or pixel analysis. It's basically it's the one I mentioned at the beginning where you would probably have to implement it yourself on your own, and this is more of a conceptual part of the presentation. So what this is basically how this basically works is most objects on the field are going to be of one color. If you think about any of the game elements or any of the field elements, like the junctions, like the poles this year are all yellow, completely yellow. Cones are either completely blue or completely red. And even if you're trying to define tape on the ground, those are all of one color too. There's not like anything that's super colorful. And therefore, it's much easier to examine the color of the pixels you find in your image to determine where objects are. So let's dive a little bit deeper to see how this kind of works on the inside. Okay, so this has several fundamental steps in order for you to be able to accurately find objects. So first, we have to be able to take images frames from the webcam. So this is going to be like taking a photo of whatever the webcam sees. Then we're going to be able to analyze this image to find out where certain components are within the image. So the first step is to filter this image, because the first image you see has a ton of different things in it. It has like cubes, it has ducks, it has balls, and it has like the whole mat with shadows and stuff, right? So we want to be able to take out the important part, take out the unimportant parts, and only focus on the parts where we want to be looking at. In this case, we want to look at the yellow objects, the ducks and the cubes, because those are easy to grab and easy to score, relatively easier to score. So we're going to filter this image, take out all of the yellow parts, and that's going to result in the final image you see. There's only white and black in that final image, and the white parts represent the important parts that you want to be examining, and everything else is basically masked out. So if you know how Photoshop works, this is kind of like a Photoshop mask, essentially getting the important parts that you want to focus on. After that, it's a lot easier to work with. You have ones and zeros, right? You can find certain specific shapes within this image, whether those be like lines, you want to find how long a line is. That can sometimes determine how big a shape is, like just like the line, maximum line, and that can determine where your objects are. So in this case, if we were trying to detect the cube, what we can do is we can try to find a line of, say, at least 15 pixels, and that would determine that we have a cube there, because there's no other object on the field or even like reflections or shadows that would break or like create a fake cube with. So there's no other way that we can have 15 pixels in a line in a row without a cube being there. So in this case, we can detect the cube just by looking at the lines, the horizontal lines. Okay, so after these 3 steps, we're going to be able to find objects in this image. You can find multiple objects by just running the shape detection over and over again, like just not stopping after you find the first one. And yeah, so that's essentially the main steps of how this is going to work most of the time. And the reason that I really like implementing it by originally is because like these shapes that you want to find in the image, they're not always going to be the same. There's not always going to be a line. It could be like other certain shapes that you want to be trying to find on the field. And in that case, you can really easily change the logic of how you're looking for shapes. And then you're going to be able to find a different object, right? And this also gives you like exact control of what you're doing with the image. Since you're literally working with the 2-dimensional array of the pixel colors. You have complete control over everything you're doing. And the third reason I kind of like to implement it by my originally is because it's very easy to incorporate into the rest of your code. You can frame the whole setup such that it fits right in with everything else you're doing. And yeah, so it's just really nice to be able to completely understand all of the code that's there. And because it's not too much code, it's really nice to be able to understand everything that's there and be able to change it however you like. And there is one sample class that you can look at that could help you know how to take image frames from the webcam. It's under FTC Robot Controller again because those are the samples, and under Java org.firstinspires.ftc.robotcontroller, and under external samples, there's going to be a concept webcam.java, and that it doesn't have anything to do with like the image detection itself, but it helps with the first step of taking the image from the webcam, which can be kind of challenging if it's your first time trying to do that. Any questions about the process so far? Okay, if not, I will move on. So next, it's important to figure out how can we do a second step, basically, of like filtering out the colors that we don't want. So naturally, when the image comes in, it's in RGB format, which means each pixel has a red, green, and blue value. And these red, green, and blue values are what determine what color it is on the screen. For example, white would be 255 red, 255 green, and 255 blue, while yellow might be a mixture of the numbers in a different way. And this is really hard to deal with because it's kind of all entangled together. Blue affects like the color by itself, like the hue basically. Red also affects what color it is. For example, if you add more red from a blue color, you go from blue to purple. So like, or you could go from black to red, or you might be able to go from this turquoise color kind of turquoise color up here to white. Like it's very hard to determine how red is affecting the color overall. Same thing with the other ones. Green could turn the blue to a turquoise, or it could turn black color into green, or it could turn red into yellow, or it could turn pink into white. So there's like a lot of different ways that just turning one number will impact the color. So that means that all three numbers, red, green, and blue, are all entangled together. So it's really hard to actually figure out what color you're looking at. Because the numbers can be similar, but the color can be completely different. So we don't want RGB. We want some other color format that might easily tell us what kind of color we're looking at. And it turns out that color format that is very helpful is HSV, which stands for hue, saturation, and value. So these three different things, not red, green, and blue, but hue, saturation, and value, they tell us actually a lot more information about what the color is. And you can search up like how to convert from RGB to HSV. I believe the Android color class also has a function to directly translate from RGB to HSV. So there's a variety of ways to do that. That's all well documented because color formats are very important in all software. And so we can take a look at why HSV is so much more like information giving than RGB is. If you look at the diagram on the right, it shows how an HSV color space works. Hue already determines what color it is. If we want yellow, we have a specific hue range. Not even looking at the saturation or the value, we can use one value to determine what color we're looking at already. So that's why it's so powerful. If we want all yellow pixels, like from the previous slide, we want all the yellow pixels, we can just filter out everything based off of one number, which is the hue. If it was RGB, we wouldn't be able to set good ranges for what counts as yellow and what doesn't count as yellow. And there's actually a lot more that can come from HSV, not just the color giving. The second, it turns out that all three values in HSV are all equally important in allowing us to like accurately detect objects. The first one is hue. Obviously, that's the most important, right? Because it determines what color we want, and that's the main part of our filter. But after that, we can ignore grayscale very easily. Like the gray mats are a huge problem if you're using RGB because they're going to have like say 150, 150, 150, and that's really hard to tell what color it is. They're close together, but it might be a little bit off, and you just don't know what color it is if it's gray. But in HSV, you can just the saturation value basically determines how gray it is, and that's just really helpful because it allows you to just use one number to filter out all the grayscale colors, which we usually don't want. So the second part of HSV is also really, really important. And the third part of HSV is value. And value basically determines how bright the object you're looking at is. So it's actually really important because by ignoring the value altogether, we can just account for different lighting situations because that's all value is how bright the light shining on the color actually is. So value helps us a lot in that way as well. Does anyone have any questions about like the color formats and why they're really helpful for us? Yeah? So is there any library that's built in that can automatically do this conversion? Yeah, so I think I mentioned a little bit earlier, Android Color. There's like an Android.color class. And if you look in here, there should be an RGB to HSV function. So let's see if we can go down to its functions. Let's see, color to HSV. Yeah, so this is one of the functions that you can use from the Android Color class. It's already provided because your app is already an Android app, but this function can convert your ARGB, A meaning like your alpha, which is how transparent your pixel is. That doesn't really matter though. It converts your ARGB, which I believe is the bitmap color that you get back, like the color format, but you can do some extra research on that. And that converts it to its HSV components, which is hue, saturation, and value. So these three. Hue will be between 0 and 360, because as you saw from this diagram, it's like a full circle. So that degree of like hue is how, like what color it is basically. And S and V are both a percentage from 0 to 1. So like how much light is there? So there's going to be a value from 0% to 100%. And how gray is it? There's also going to be a value of 0% to 100%. So those three numbers are, it's basically how it returns back. And if you would like to do it yourself, it's actually not bad at all. So there's only a bit of logic. So after you have your RGB, this is from online. So you're probably going to be able to find it in a lot of places. You can just search up like code to convert from RGB to HSV. And once you have your R, G, and B values, you can just run this program to convert it to HSV. I have no idea what it does, but it works. So it works. So it's really nice. But yeah, I guess that's just how the color spaces work. And yeah, so this is just the relationship between RGB and HSV if you want to look at that. Yeah. Any more questions about like conversion or why we're using it? All right. If we're all good, then I'll keep going. So the last part is basically finding the information. And a couple of examples of ways you could do this. I mentioned one of these earlier. One of these ways is counting the number of colored pixels. So if you recall from earlier, last year's parking was determined by which tape marker is covered. Obviously, if a tape marker is colored, say a blue tape marker is covered, there's going to be less blue pixels in that area. So what you can do is split your image into multiple areas and then count the blue pixels in each area. And whichever area has the least blue pixels is the one that's covered. The ones that are uncovered will have a lot of blue pixels from the tape. So this is actually the way we detected which marker was covered last year. So it was really nice for us because instead of detecting the object we placed on top, which is what a lot of teams did, we were able to just detect the markers, which means we would be able to detect the parking placement no matter which marker was covered, right? Or not no matter which marker was covered, but no matter what object we use to cover the markers. We can use like, we can cover with our hand, or we can cover with someone else's object or our own, or we could cover it with basically any object that's not blue or red because that interferes with like the tape colors itself, right? So the counting would be off. But anything that wasn't blue and red, we would be able to use, and we could just basically swap it out whenever you want without changing the code. And that was just a really nice extra feature to our code last year for us, especially since one of the strategies last year was for one team to provide two objects for their own alliance. So because of this code, we were able to use the strategy even better with any other team, because we were able to detect their detect the barcode no matter what. And the second one is to find shapes of colored pixels. So counting colored pixels is relatively simpler, because all you have to do is count the number of ones within a certain range. Finding shapes is a little bit more complicated, but essentially it's the same algorithm in the end, because it's still a brute force algorithm. You're gonna like loop. There's definitely optimizations that can be made, but one thing you can do, especially with a smaller image size, you can loop through every possible starting point and check if the shape is present in that starting point. And yeah, so in this case, if we're looking for a line, we can loop through every possible starting point of the line and see if there's a valid shape that's all in a row. Some other optimizations you can do for this is you could find what percent of it is correct, of the shape is correct, and for example, what percent of ones match where it's supposed to be. And if you have a high enough percent, maybe you can assume that that's where the object actually is. So that's just one example of how you could find a shape within the 2D array of zeros and ones at this point. Remember, we have zeros and ones because we already filter out all the unimportant information to us, and we're just left with like the pure stuff we are interested in. Okay. Other stuff you can do is optimizations. I kind of mentioned earlier. One very, very easy optimization is just scaling the image down to a smaller size. Time is of an issue here. If you use a 1920 by whatever 1080 image, obviously looping through it and like checking for the shape is going to take a super long time, especially if your control hub is running, or like your robot controller is running other stuff at the same time while you're trying to compute this like heavy computation and stuff. We don't actually need that high resolution of the image. Nobody's looking at it. Only the computer is trying to figure out where stuff is. As long as you don't have like a 1:1 image, you can have, I think what we used during the competition was 640 by 360, which was small enough for it to be fast. You can even scale it down even more by maybe 2 times or 4 times, and it'll be a lot faster. So that's one really, really easy optimization that you're going to be able to make. But one important thing to remember now is once you scale an image down, your shape will kind of change, because like the dimensions of the shape are going to change. If you're looking for a 15 pixel line earlier, maybe you're only going to be looking for a 7 pixel line now, because there's just less pixels. And another possible optimization is multi-threading. So each CPU of a computer actually has multiple threads. If you stick to the main thread, which is where most of the program is running, you're going to basically stall everything else on your robot until you're done processing this image. One thing you can do to mitigate this is basically creating a new thread, which is basically creating a new direction for the code to run, and that code will run simultaneously with your main thread code, which will basically put it in the background and make it not affect any of the other things that you're doing. That way you don't have to wait for this image to be done, even though it should be decently fast. So this image processing is better to put in the background thread, just because it's relatively computational heavy, and you don't really want it affecting your other stuff, and there's really no reason for you to have it affect your other stuff. Does anyone have any questions about optimizations, about finding information within our new array of zeros and ones? Okay. So this was an example I already gave, but it's of the tape markers. So last year, this is kind of what you can see, what the camera can see, or what the camera can see after we crop it out. And I forgot to mention, but another benefit is that we can basically focus the camera really easily on an area that we want to look at, because the image is super big. It might capture stuff in the background again, like I mentioned for the TensorFlow. that might not be very good for us to look at. Because it might confuse the algorithm. Here we directly focus the camera up on just those 2 tape markers. And after that, we can do the pixel counting to determine where the markers are. So we kind of split this image that we get in 2. The one on the left side, you can see have a lot of 1s where the marker is. The one on the right side has a few, because you can see the object we placed on top was a little bit see-through. So there's a few there, but it doesn't pass our threshold because it's very obvious that there's not enough 1s to be counted as a marker. So there's going to be some like noise, I guess, in the data, but that's not enough to throw off our algorithm. So this actually worked really, really well for us last year. We didn't have any problems with it. Yeah. So any questions on like other applications of this, or? Okay, I guess in that case, I can give like another example. This year, we were able to detect junctions, which are the yellow poles, and cones in our autonomous and in our teleop to help us speed things up. So this is kind of like what the HSV filtering looks like for different colors. So on the left side, even with stuff in the background, right? I'm sorry, on the upper one, even with stuff in the background, once we filter out yellow, we kind of get a really good boundary of where that pole is. And it's pretty easy to check where the pole is within the image. Again, you can look for a line, you can look for a vertical line, or you can look for like a rectangle if you wanted. There's a lot of stuff you can look for within the image to prove that there's a junction there. And once we know where it is in the image, it's just a matter of finding out like that calculation step from the image to the real life coordinates, and that's how we can move the robot to get to the right position. Same thing with cones. We can detect like the cones. You can see it's a little bit more difficult because the cones are relatively bigger, shinier, and they kind of reflect light. But the main part of the cone is still there. You can see there's like a little bit of noise on the top right of the cone. It's where it doesn't think it's blue, because if you look on the left side, you can see that there's kind of a reflection of light and it's really bright. So it's counted as grayscale, but it doesn't really matter in the long run because we still get this big chunk of like data that allows us to know, okay, the cone's there. And then after that, it's just a matter of adjusting your robot to match where it is. Yeah. So this is kind of like the more applicable way in like actual teleop and stuff. So any questions about this? Okay. Any questions overall about this whole process of like the image processing and whatnot, or is all clear? Okay. So I guess we can move on to other used tools. This part's going to be relatively short because it's like the concepts were kind of covered already. It's just like how you implement these concepts again. So OpenCV is a very widely used tool by many, many teams. And there's like a really, really good OpenCV library called Easy OpenCV. This is made by OpenFTC, which has like an OpenCV platform which is compatible with FTC, like because OpenFTC is in the name. So but in terms of the algorithm, not only does it have like the pixel analysis kind of thing, it has like a similar HSV filtering method. If you look in a lot of like people writing about this, they have like images. You can see there's also a masking ability that this has. So it has a lot of features. So it's a lot better than TensorFlow in that way. It has a ton of features you can use. You can do stuff like display the active camera stream, like all the frames that you get in the camera. You can display them on the driver station. You can display them on the robot controller. You can even draw rectangles wherever you want on the image, like to show what you're looking at. Like you see here, there's like rectangles drawn around the stones. And on the blacker parts of the stones, you can see that there's a more constrained border around that you're looking at. Yeah, so you can just draw stuff and like re-upload it to the driver station so you can see exactly what you're looking at, exactly what the program is looking at. So it's really good for debugging in that way. And yeah, you can also do stuff like there's just a lot of functions. You can look in the GitHub repository. There's a lot of example code. And when you look through those, you can find a lot of the functions that are useful with OpenCV. OpenCV is widely used, as I said earlier. So there's going to be a lot of people making videos about it. There's a lot of documentation websites online that talk about it. So it's pretty, I guess, simple to learn and start doing. If you don't want to make your own implementation of like image processing, OpenCV is a very good alternative and very powerful as well. Yeah. So the only drawback I would say is like you don't have like complete control. There's a lot of features, but say you want like some specific feature that like goes beyond that, then you can't like make that. But in general, like 99% of the cases, 90% of the cases, your OpenCV is going to be enough. Yeah, so that's like maybe the only drawback of OpenCV. But overall, it's a really powerful platform that's I guess easier to learn. So if you're looking to start using robot vision, OpenCV is a very good place to start. Okay, any final questions before this ends, I guess? Yep. Sorry, what did you say?
How do you train all of these things?
Oh, like training? So like OpenCV? Oh, those don't require training. Because they're usually like you creating your own algorithm, like your own pipeline it's called, to that's kind of like the logic behind what's an object and what's not. Like you kind of determine that yourself. And that's usually very accurate because like I said earlier, the field elements are actually a specific color and a specific shape. So those things you can kind of determine by looking at the pixels, and you don't really need like say an artificial intelligence training like you usually would.
I mean, if you provide those free resources to train, right?
Yeah. Oh, those training.
It's not there. They all need.
Wait, are you talking about the this slide? Yeah, so if you want to train your own custom TensorFlow models, then that's basically, these websites are where you're going to train them. It's free for like a limited amount of time. Like you get a limited amount of training time, which is basically like how long your models are training on their server for. So like how many resources you can use. There's basically a limit to that, but it is free to use, and there's more than enough time for normal use.
Okay, so you have to train all of these things.
For the other algorithms, you don't really need to train them. It's not TensorFlow, but if you want to train your own custom TensorFlow models, then these websites are really good.
Second question, are you going to share the
Oh yeah, I can share this presentation. I don't know if there's a list of like people who attended this, but or like the emails, but I can send out this presentation. Yeah.
can send a copy to my email? Share with my team.
Yeah. I think there's definitely like you put your email down when registering, right? So I think there might be a follow-up email after this event. I can just ask Isha to attach this presentation as well to that email, that follow-up email, so everyone can get it. No problem. Is that all the questions? Okay. If so, I guess that's the end of this breakout session, and the next one, I'm not sure when the next one starts, but y'all can just chill until the next one. Hi.
If everyone could make their way to a breakout room, we're going to be starting in just 1 or 2 minutes. Thank you. Attention, everyone. We're going to be starting with our breakout rooms. So if you can make your way to one of the 3 breakout rooms. Thank you.
Testing, testing. Hi, everyone. We are starting the second. Hello, hello. Starting the second session for breakout. So if you guys can please choose your sessions, and we'll be starting soon. I'm gonna take that to the kitchen. Oh my gosh! Actually, let me grab Oh, maybe someone in coffee. Yeah. Okay. It's okay. Don't worry about it. Well, I think we need it for the fridge. Do you want me to get you another water?
No, it's fine. Hi guys, welcome to the second breakout room. And if you haven't moved to a different one, if you wanted to, or join a different breakout room, this is the second session. So this is the second session. So yeah, feel free to go to a different one if you are planning on doing that. Yeah. So in this breakout room, we're basically going to go over a brief introduction to robot vision, and how you can use that to basically leverage the information on the field that you get from the webcam to make decisions on where the robot's supposed to go. So today, we're mainly going to talk about 3 different robot vision techniques. The first one being TensorFlow, which is the machine learning, artificial intelligence library that when you give it data and models, it will be able to tell you what objects it's seeing and where they are within the image. The second one is more of an original algorithm. I would recommend if you were to try to do robot vision this way, you would have to write most of the logic yourself. So if you're just looking to start on robot vision, you're just wanting to try out some things, I would recommend using the other ways. And the third one is using other tools, mainly OpenCV, which is basically a less flexible version of the second one, because the second one's written by yourself. You're able to change it however you like. If you were to use OpenCV, there's a wide range of tools that you have access to. But once anything beyond that, it's kind of hard to do. But it's a really good starting point, and it does have a lot of tools that will cover basically 99% of your use cases. So if you really, if you're just starting out, OpenCV is a really, really good option. So, and we'll cover that at the end. Okay, so for the first part of this, we're going to look at TensorFlow, and this is going to use the Vuforia engine, which is also a different image processing engine, except this is mostly going to use Vuforia to open the camera stream and stuff. So for TensorFlow, we can dive a little bit into how the logic works in terms of how we use TensorFlow and that kind of stuff. So TensorFlow is going to use something called a TensorFlow object detector, which is basically TensorFlow but ported onto the FTC SDK, which is already done for you, by the way. It's already in the library when you download the FTC SDK. You have already the TensorFlow object detector that works. All you have to do now is give it a TensorFlow Lite model. And some TensorFlow Lite models are already provided by them. Each season with new game elements, they develop a model and they push it out with the SDK for you already. So that's really nice of them to do. And like if you're just looking to see how a TensorFlow is working, then these default models that they give you every year are a really good starting point to branch your knowledge off of and how you can use these things. And there's also a basic sample program that they have already there, utilizing all of these things together with the models, with the object detector, everything, and setting it up and everything. So if you want, oh yeah, question? Oh, okay. So what are we trying to look at? So that kind of depends on what you're trying to achieve. There's always like game elements on the field, like the cones this year that we're trying to deliver, right? Maybe you're trying to find where those are, right? You want to detect those. Last year there was different game elements. There was cubes and balls, so maybe you're trying to detect those. This year, at the beginning of the match, you actually have to look at like a specific object and then determine what the image on like the object is. So there's like 3 different images that are randomly given to you, and you want to be able to determine what the image on the object that you're looking at is. And TensorFlow is a very good option if you're trying to consider how to do that. Yeah, good question. Yeah, so if you were to try to see how everything bands together in the FTC library, there's a nice sample class they give you under FTC Robot Controller and Java org.firstinspires.ftc.robotcontroller. Under external samples, there's a concept TensorFlow object detection class that kind of bands everything together if you're looking at it for the first time. Okay, let's next go to what the TensorFlow object detector actually tells you. So recognitions are a class of like objects. They store a bunch of data about the objects that the TensorFlow model is seeing. So every time you want to see what the TensorFlow model is really giving you, you can call a function called getRecognitions, and this will return a list of all the recognitions that the object sees on the image. On the image on the right here, you can see that there are 2 ducks within the image, and each duck is bounded by a box, signifying that the model recognizes it as a recognition, as an object that it sees. So on the right here, there are 2 recognitions. If you were to call getRecognitions on this frame, the model would return a list of length 2. And each object within that list is one of these ducks. And of course, it just doesn't tell you how many objects it sees. Each object has its own information within it as well. And some of the important information that you can get from these objects, number 1 includes the label of the objects, which is basically what type of object it is. On the right side here, you can see both of these objects are labeled by duck and then a number after it. The duck part is the label. If you were to look at, say, cubes, it would say cube. Of course, this has to be trained within the model, but every object that it sees that was trained within the model, it will tell you what type of object you see. So if you were to do the 3 image thing from this year, where you look at an object, determine which one of the 3 images you're looking at, you would probably have to train 3 images in a model, and the label 1, 2, 3 would probably tell you which image you're looking at, and after that you can decide what to do. So that's like for an example from this year. Another thing that it gives you that's pretty important sometimes is the bounds within the object. Sometimes you want to know not only what type of object you're looking at, but you also want to know like where the object is within the image. And it's during these times where looking at the bounds can help. So the bounds basically give you like the left, right, top, and bottom, like in terms of like coordinates of the object. And this really helps you when you're trying to decide where the object is. Maybe there's some circumstances where you want to see where the object is. Maybe you want to drive to the object, right? That's one use case. Or maybe the position of the object determines like something instead of like which one of 3 images you're looking at, like I previously mentioned. The third thing that's really important is the confidence level of each recognition that the model has. So each recognition, the model can never be 100% certain that that's the object, right? There's always something that throws the model a little bit off. Maybe it's like the lighting, the angle, whatever. The certainty that the model has that this is an object is not always going to be at 100%. That's what these little numbers on the bottom right of each duck are. So the first duck on the left is going to be 96% certain, says the model. So basically, it is a duck. The one on the right is a little bit less certain, probably because it's at a worse angle for the model, maybe because the lighting's a little bit different, or maybe because it's a little bit further away than the one on the left. There's a variety of reasons that the model might think, oh, this is less likely to be a duck. But again, it's 90%, so it's pretty good. So it's going to be a duck. There's a function within the TensorFlow object detector. You can set what the minimum confidence you want it to have before returning it as an object is. And in this case, 80% might work well, 70% might work well. Kind of depends on what conditions you're performing this in. Yeah? Yeah, that's a great question as well. So First does provide some models. The one I'm showing here is provided by First. A lot of models, if you want to extend to like your own images this year, for example, when you detect the 3 images, First provides like a default 3 images, and those are already trained by TensorFlow that they provide you as well. If you want to earn more points by putting your own images on top of those instead of using their default ones, then you would have to train your own model or use a different way of detecting. For example, scanning QR codes maybe, which has a lot of libraries in place already. Any other questions? Yeah? Okay, so for the images, let me see if I can find a picture. So the images I can kind of describe them right now, but they were essentially like small solar panels or like light bulbs or these like lightning bolts kind of. Let me see if I can find it really quickly. If I can't, we'll just move on. But there's like a default like 3 images they give you. Oh yeah, it's right here. So these are the 3 images that they have trained already for you. So like those lightning bolts, the light bulbs, and the solar panels. So these images are on this cone, as you can see here. At the beginning of the match, they will rotate one random side to face towards you, and you have to be able to determine what side is on. But luckily, they provide a TensorFlow model already for you to be able to detect these. And like I said earlier, if you want to earn more points, there's this task you can do this year. You can put like your own images on top of these 3 images and be able to detect those because you don't really know what side they're on. In that case, you would have to train your own new model. And there are tools that First provides to do that for you for free as well. So it's not too hard to do. But I'll explain some like drawbacks of that and stuff later as well. Okay. Any more like questions about what the model returns back to you or how like the model initially works by itself? Okay. If there are no more questions, I can move on to like several examples. So one of these examples was from the previous slide. Last year in Freight Frenzy, they provided a TensorFlow Lite model which allowed you to detect the cubes and the balls, which were the game elements last year, as well as ducks, which was also part of the game last year. These rubber ducks they had in the game, and you would be able to detect them with the TensorFlow model. Yeah, and that's like the main things that they gave you already to be able to detect. It wasn't super accurate last year because those like things are kind of far away from the robot most of the time, and that makes it a little bit less accurate. But they still did provide you it last year. 2 years ago, the game was mainly played with like rings, kind of like donuts, and you had to like shoot out the rings from the robot into like a goal, right? And they provided a TensorFlow model to be able to detect ring stacks of 1 and 4, which was the initial detection that you had to perform. So like they gave that to you as well. Yeah. So that's just an example of some things they might be able to give you at the start of a season. And if you want to like extend off of that, you can create your own models, which I'll talk about on the next slide. So any questions about like default models that they give you, anything provided? Yeah? Yeah, that's a really good question. So a lot of times, like it doesn't usually mistake objects, but sometimes based off of like the lighting or like the angle, it might not see the object at all, which is completely like understandable, right? Because no way it can see everything in all circumstances. Usually, the thing is with there's like an initial detection every year before the game starts. You detect something on the field. That's what I can go back. I don't know if I can go back, but that's what the images on the cone were for. Oh, yeah, I can't go back, but that's what the images on the cones were for. They were there for you to detect before the game. In that case, it's very accurate because all the scenarios are the same at the beginning of the game, because your robot's always going to be in that position. It's always going to be looking in that direction, right? Everything is stable at the beginning of the game, which is why TensorFlow works best at the beginning of the game. After that, robots are all over the place. Your robot might be facing a different angle, and it might be further away from the objects you're trying to detect. So there's a lot of more factors after the game starts. So mainly, it works before the game, and that's the best place to have it. And yeah, the only times we've used it is the initial detection I just mentioned. Any other questions? That was a good question. Okay, if not, I guess I'll move on to training your own models. Okay, so there are times where you want to train your own models. For example, this year, where we had custom images on top of the default ones. So we wouldn't be able to detect them with the default model. Obviously, they weren't trained to detect it like that. So for custom TensorFlow models, the first point I want to make is that internet is a great resource. There's definitely a lot of custom TensorFlow models out there. Not all of them will be like compatible with the FTC TensorFlow object detector, which is a very, very big thing that I want you guys to remember, because yeah, there's just a lot of things that aren't compatible. For example, these have to be TensorFlow Lite models, which is a very specific type of model. It's relatively lightweight, so the control of it, which is not a very powerful computer, will be able to run it easily. And not only that, I don't know, I'm not completely sure about what extra compatibility issues there are, but I tried like tuning like a standard TensorFlow Lite model with like the standard ways that Android might tell you how to do, or like Google might tell you how to do. Like following those steps, it ends up not being compatible in the end. So there's going to be issues with that if you're going to tune it, if you're going to train your own model in a standard way. Luckily, there are ways around this. The best thing to do in these cases is to look at the first tech challenge machine learning toolchain, which is a new tool they released just this year for you to be able to train your own TensorFlow models. And it's really nice because it's really, not only is it easy to provide data for and very easy to train, it also allows you to create a model that's compatible with the FTC right away. Like you don't have to worry about compatibility issues at all. And it's also free, provided by First. Yeah. So if we take a look at the website, this is kind of what it looks like when you log into the website. You can see that there's a bunch of models that we've created so far. If we click into one of them, you can see this is kind of how you're going to train it. So you're going to take, instead of, usually when you train TensorFlow models, you provide it a big data set of maybe tens of thousands of pictures, and also like the answer, like, which is basically what object am I looking at in this picture, right? That's like basically not possible here because we don't have tens of thousands of pictures. We don't have the time to label tens of thousands of pictures either, right? We don't have that many people or resources. So this makes it really simple. Because all you have to do, instead of taking that many pictures, you can just take a video, because a video is basically a lot of pictures combined in one. Each frame can be its own data point. And the big point is, however, that you want to change the lighting. Like you see, like you saw there, it just got a little bit brighter and a little bit more brighter, right? You want to be able to change the lighting around, change the angle. Yeah, and after you change the angle again, and then after like looking around the object a little bit, changing the lightings a little bit, it'll basically provide a pretty good data set for what the object is. So that's a good data set. But how do we provide like the labeling, like I was talking about earlier? We can't go through and manually label every frame. So this is where this tool really comes in use. So if you hover over, you can actually see like a crosshair up here. So if you drag, you can actually sort of create a bounding box around the object. So in this case, we already have this bounding box over here, and we've labeled it with robot because that's the robot. And as you can see, as I click through, the bounding box actually moves with the robot automatically. And this tracking is provided by OpenCV. Again, I'll talk about it later. And you can change the algorithm around, but it doesn't matter a whole lot. Just make sure that the box is staying with the object that you selected. So it will automatically move through with you. You don't have to change the box at all. And this is basically the automatic labeling that this tool provides. So it's really nice. You only have to take a video and then make a bounding box rectangle around it. And after that, you just have to monitor how it's doing and make sure the box doesn't go off the object. Otherwise, the data could be messed up. So yeah, after this video, taking a video and uploading it, it'll automatically train it on their server for you. And then when it's done, it'll return back as a model. So it's really, really nice. I do want to point out, it's not unlimited use. So there's a very generous limit, but you can't be like training models every day because like it takes a lot of resources for them and a lot of money to be able to provide this tool at all. So it's really nice of them to do that, but yeah, there's not a limited use. Otherwise, it would just be too costly for them. And so I would advise like if you use it in like a normal fashion, like you maybe train a couple models maybe every few months, right? That's fine. But if you go like if you're starting to train models again and again and again and again, testing again and again, I would say like that might go over the limit at some point. I think there's a little bit more like maybe in the user manual of like what the limit exactly is, but I would advise like not just like abusing the tool and using it over and over again. That being said, it's also probably better to decide a good set of objects to train it on before going forward with it blindly and then checking how well it does. And what I mean by like a good set of objects, you probably want like some significant difference between each object. Maybe like different colors, like completely different shapes, different patterns. All of that will help the model perform better. So, so that's just a couple like pointers I want to give on this tool. Question? Yeah. So for each object, you just probably want to take a video, maybe like move a little bit of the angle around, not too much because that might confuse it a little bit. And you probably also want to change like the lighting scenario a bit. Maybe you shine a light at it to make it brighter. Maybe you turn off, or maybe you can make it darker, cast a little bit of a shadow over it. That just like gives it more data so that it can recognize it in more different circumstances. Yeah. Yeah, it's definitely a big difference. I know a lot of teams that have been messed up by the lighting, especially like at states, because it's not like a big gym and they light it up completely like with ambient light. It's like a really dark room and then they shine a big spotlight on the field. So it's like a completely different type of lighting. It messes up some teams. The TensorFlow worked reasonably well for us during states. But yeah, the lighting does change a lot and it's very important to consider. Yeah? Yeah, so it's like, there's like a big room, like an auditorium kind of, and the lights are basically off, except it's like the Amazon building. So they have a bunch of spotlights that shine down on the field. And that big spotlight is it's not like ambient light anymore. Ambient light is all around and everything's illuminated, everything's bright. That one's just like one big flashlight shining down on the field. I'm not sure how you'd be able to mimic that, but yeah. Yeah, it's still bright. It's just not the same type of bright, if that kind of makes sense. The other thing I would say is like I'm not sure if it's going to be in the same building every year. So next year it might not be the same lighting circumstances, but it is good to consider different lighting circumstances no matter what, just to make it more accurate. Yeah. Any other questions? Okay. So I guess I can give another. Yeah. Okay, that's the question slide. Okay, I guess we can skip that then. But here are some reasons why you might not want to use TensorFlow. Like I said earlier, it gets kind of weird when you're like in the middle of gameplay and all the robots are just running around. You don't know where you are completely. It just gets weird. If you're really far away, it doesn't really perform very well. It's hard to see like the pattern from far away. So like if you're like 2 or 3 tiles away, like 4, 5, 6 feet, it might start getting a little bit shaky. The lighting, like I just mentioned, matters. Maybe not a whole lot, but it does matter to some degree. There's also like an inaccuracy sometimes based off of like the angle that you're looking at it, or maybe the bounding box might be a little bit off. So if you're really stressing where it is within the image, then you might not want like TensorFlow. It will be mostly accurate, but there's just like a lot of, it's just not very robust in a lot of settings. So that's why it's usually good to use it at the beginning of autonomous if you're going to use it. But after that, it might get a little bit shaky. And it's also quite inflexible. They give you a bunch of data about the objects, but that's basically all you can get. Like you can't manipulate the data, or you can't really manipulate the data like before it returns. You can't really do anything to change how it's like given to you, right? So that's very inflexible in that way. It just has those datas. And also the very, very time-consuming part is, well, not really time-consuming, but like you have to train a new model for every new object you want to detect. And that's just a little bit annoying because you got to like pull out the phone, record, like upload it, and then wait for it to train. And training actually takes a while. And so just that inflexibility might be a little bit a reason not to use it. Yeah? Sorry, I can't hear you. Oh. Okay, yeah. That's a really good question. So there's a couple more ways to be able to detect objects, and we'll go over those next in the next few slides. TensorFlow is definitely not the only way. It's just one of the many. Yeah. Yeah. Oh, okay. So like the rules change every year, but the main format's always going to be the same. So before autonomous, you're always going to have like when you're going to click like initialize, and in that initialize stage, you're not allowed to move the robot. Like there's like you can move the robot a little bit, like to initialize all the positions and stuff, but you can't move it a lot. So in that initialization stage, that's when most teams will detect the initial thing. There's always something you have to detect before the game, or at the start of the game rather. In every competition, every year they have that. So that's when that happens. And then you're going to have a 30-second period where the robot is just driving on its own. Other vision techniques are really useful in that period because obviously there's no driver control. So it's really useful to be able to adapt to your circumstances because it's not always going to be the same 30 seconds. It's going to bring in a lot of different scenarios, and you want to be able to adapt to those as best as possible. So the other ways I'm going to present later are going to be very good to use on those. Yeah? Not really. It's like we have parts that are not robot game. For example, we want to connect to professionals. Like we want to get mentors. We want to get sponsorships. We want to connect to the community as well. Like just that kind of stuff. It's not exactly like a whole project thing. And if you really like don't want to do it, you don't really have to, I guess. But it's always good to be able to give back to the community and just like do that kind of stuff as well as doing the robot. So yeah. Yeah. There's a lot of circumstances where TensorFlow is good, but there's also a lot of circumstances where I would not recommend TensorFlow. So it really depends on what you're trying to do and when you're trying to do it. It's very accurate in some circumstances, but in others it's not very. So yeah. Oh, this year up to now we use TensorFlow for the initial detection. So yeah, we did use it 2 years ago. The only detection we did was TensorFlow. So yeah, we do sometimes choose that as a very good method to use, but it's only in certain circumstances. In others, we would be able to choose other methods, and they don't restrict you, so you can do whatever you want. Yeah, exactly. Yeah, you do whatever fits. Yeah. Yeah, so we have like each person has a booth, and you don't necessarily have to have a trifold. You probably want something to show other teams what you've been doing and learn from other teams and stuff. So that kind of stuff you want to have in a competition, just like showing what you've learned this season, what other people might find interesting, that kind of stuff. Yeah. Okay. If there are no more questions, I guess I can move on to more types of robot vision that might be more suitable for other circumstances, and we found work in a lot of different circumstances as well. So the next one is more of you create it type of vision. Like it's not really given in a library. There are obviously libraries that kind of leverage this type of algorithm to detect, such as OpenCV. But this is like the most flexible. Since you're like writing it yourself, if you want to use it, you can basically add whatever you want to it. You can change it however you like. It's very, very flexible. You can fit it with the rest of your code very easily. So that's what we're currently mainly using as our vision. Like last year, all of our vision was done in this way. This year, everything past the initial detection is done this way. So yeah, it's very nice. So before I get started on like the process on how this works, this is mostly conceptual. There's not really like library or examples that you can use. I can send like a link with some like a skeleton code for this, but it really depends on your use case and how you want to incorporate it with your code yourself. So like the main conceptual way is like just that, and then that's like you build around it to fit your needs, which is what we've done. So firstly, the only reason this works is because FTC, the game elements are mainly only one color. As you can see from the cones that we had over there, they're only blue or red. As you can see from these ducks or the cubes or the white balls, they're all like one solid color. Or like even the pole we had over there was red. The official pole is all yellow, but still one color. You're never gonna have a very colorful object. So this means this is mainly color-based. It does take shape into account, but basically the main way this works is by color. So it works really, really well in FTC. Every year they have like the game elements, they're all gonna be of one solid color. So they're gonna be quite easy to identify just based off of color. After that, you can provide some other like functionalities to be able to deal with like maybe noise within your image, like something that appears to be that color but it's not really. Like you can deal with that later with like shapes, but those are relatively simple shapes, and the main part is with the color. So the 3 steps is first you want to be able to take image frames from the webcam. So this webcam, usually teams will have a camera connected to the robot via USB or USB-C, whatever. And you want to be able to take images from that webcam and take like basically a photo. You return basically a bitmap format, which basically is the most fundamental format to store like each color of each pixel within the image. After that, you want to be able to filter the image, decide which pixels are the color you're looking for, because like I said, there's always one color that you're going to be looking for within the image. And then at the end, you get a black and white image, right? So it's either 1 or 0, and either the color that you want or the color that you don't want. That's really easy to analyze. You can detect shapes within that. You can count the number of white pixels or the number of black pixels, whatever. There's just a lot of ways you can manipulate that in the end. Okay, any questions about the main process before we dive into the details? So this is one of the alternatives to TensorFlow if you didn't want to use TensorFlow. And this is fairly more accurate because it's fairly simple compared to TensorFlow. Obviously, no machine learning, no AI involved. So yeah, it's more accurate in the applications that we're going to give it within the game. So any questions about this? Okay. Next, there's an example program of how you can get stuff from a webcam, and that's under one of the external samples within the FTC SDK that they give you to download. It's called conceptwebcam.java. Like they have code for how to pull the image from the webcam, because it's not like trivial, right? It takes a few steps, and it takes for you to know how to manipulate like the hardware as well. So that's an example you can follow along with if you want to know how to pull the image from the webcam. But the next step is to filter the image, get rid of the colors that you don't want, and keep the colors that you do want. So bitmap comes by default in the ARGB color type, which is representing like the transparency, and then the red portion of the color, blue portion of the color, and green portion of the color. Obviously, any color can be made up of like red, green, and blue components, and that data type kind of tells you how much of each you want in there, right? But the main problem, RGB is really, really, really hard to deal with. If you increase blue, you could go from green to turquoise, or you could go from yellow to white, or you can go from red to pink. You don't know how it's changing the color just based off of changing one parameter. Same thing with the other ones. So they're all tied together in various ways, and it's really hard to tell what color like a certain triple of red, green, and blue are. So to fix this, instead of using this in RGB format, we actually switched to the HSV format. And HSV stands for hue, saturation, and value. And this format's really, really nice because each component of HSV actually tells a lot more about the color than RGB does. Like, what does R tell you in RGB? Like, it's really hard to quantify that type of information. In hue, saturation, and value, the basics is that hue tells you what type of color it is. That's really good already because we want to figure out what type of color it is. Tells you whether it's yellow, red, somewhere in between, right? Saturation will tell you how gray the color is, like how much color is in that color. So if it's more gray, then the saturation is going to be lower. If it's really, really blue, like the bright blue that you always see, it's going to be all the way out there. Saturation is going to be 100%. It also tells you how brightly lit up it is. So that's really good because we want to be able to account for different lighting situations as well. So it kind of like filters out the different properties of the color into 3 separate parts, which is really, really useful for us. So just to recap with like more details, with a hue, we're gonna basically do the main part of the filtering. We want yellow pixels, we're gonna have a range of hue. We're only looking at that parameter. So it's really, really nice. To ignore grayscale, the mattes in the background are all gray. The hue is kind of undefined because it's completely gray. There's no hue at all. But we can ignore grayscale by basically setting a range of saturation we want to get rid of as well. If the saturation is too low, we know it's gray. We know it's matte, right? It's not the color that we want. So we can also ignore a grayscale using setting a limit on the saturation. And for value, we can just ignore value because we want it to be able to work in all lighting circumstances. Maybe you can set value to a small limit, like anything above 10%, because you don't want it to be black, because that's like no light at all, right? So you want some amount of light, but basically you can ignore lighting by mostly ignoring the value, like the V part of the HSV. So by changing it from RGB to HSV, we get a lot more information about what the color is like, and this allows us to effectively filter out everything we don't need in any circumstance. So any questions about that step? Okay, so the last step is going to be finding the shapes from within the image. Oh, and here's the code to convert to HSV. There's also like Android has a color class, and that has like a color to HSV function you can use. I haven't like confirmed if that function works with like the bitmap that you get returned, like if that's the exact same RGB format, because there's a lot of different RGB formats, maybe to fit into different sizes of integers, like 4 bytes or 8 bytes, whatever. So I just used a custom HSV conversion algorithm. These types of things you can find online, and you can confirm whether they're correct. I'm pretty sure the color to HSV works also, but I just included this in case you wanted this. Okay. So the third part is going to be about just finding the shapes within the image once you have that 2D array of zeros and ones after filtering out everything. This is basically creating like a color mask. You all like colors that are useful for your information is going to turn like into a 1 maybe. All the colors turn into a 0, and you basically have a very simple like Boolean 2D array after that to work with. So there's a couple ways you can use to find information after you have filtered out everything. I kind of briefly touched on these earlier, but the first easiest way is to count the number of colored pixels within a certain area. So last year, there were basically 3 tape markers on the ground, and we wanted to find which one was covered by a specific object that we choose. What we did was we basically counted the number of blue pixels in each area, and that kind of determined whether it was covered or not. Obviously, if it was covered, there would be a very low number of blue pixels because you can't see the tape anymore, the blue tape. If it wasn't covered, we see a large amount of blue pixels because there was a tape marker there that provided those pixels for us. You can kind of see this on like the top image here. The one on the left has a marker because you can see like there's like a almost rectangle, a square that's like from an angle. You can see that there's a tape marker there, and on the other side, you see that there's no marker there because it's been covered. You can still see there's a few ones in there. Like there's a little bit of noise, like I said earlier, but like it doesn't pass the threshold to be considered as uncovered. Yeah, so we can kind of find where things are being covered, where the colors are disappearing there, and that's just probably the simplest way of counting colored pixels. Another way of finding objects would be to look for specific shapes, like I said earlier. You can look for whatever you want. It's just a matter of like looping through the array and like finding if the shape matches in that way. You can also extend this by saying what percentage of pixels match, right? How many ones should be ones and are ones, and how many zeros should be zeros and are zeros. So that percentage can give you a rough idea of how accurate your shape is. Sometimes they don't have to be complicated. Last year we were detecting cubes, and a main problem we had with cubes is that they have this, if I can have a better image, they have these like 3x3 grid on some of the sides, so it's not always going to be the same shape. To combat this, what we basically did, instead of detecting like a whole square of ones, we just detected a whole line of ones. And this still works because nothing else in the field was yellow. Nothing else would create like 15 ones in a row. So we know once we find that, we have a cube. And this works on even like cubes rotated such that 3x3 side is facing us. You still see those like a white line going horizontal. So that's really effective in determining cubes of all orientations. So there's different ways you can kind of like manipulate this. Like I said, this is much easier to manipulate because it's your code. You can change it however you like. And yeah, that just really helps out when we're trying to like detect different things. And don't just get stuck on like detecting one specific shape. Sometimes you want to alter it a little bit. Sometimes you don't need that much. Detecting a line is much faster than detecting a cube, like a whole square, because it's just less pixels. Like if it functions the same, sometimes you don't have to like do the original shape. You can detect other things that mean the same thing. And talking about speed, this is actually a very big issue, like how fast you can detect. On a normal high resolution image, it's usually like 1920 pixels by 1080 pixels, right? That's a huge number. If you count the number of total pixels in there, that's something like 2 million, right? And that's a lot for a computer to go over, especially if you're not only looping through that, but you're also, for each position, you're also trying to find a shape there. That can take a long time. There's definitely like algorithmic optimizations that can be made, but other ways you can easily optimize is like reducing the image size. You don't actually need to look at a high resolution image. There's no one that's gonna get offended if like they see like the edges are blurry, right? Because only the computer is looking at it. So a lower resolution image is perfectly viable. For us, we mostly stuck with a 640 by 360 image, which took around maybe 50 milliseconds. If you wanted to reduce that time easily down even more, you could even reduce it down by like 2 times or 4 times or something, whatever. So just that's like probably one of the most easy operations. One of the most easy things you can do to help optimize your algorithm. And another thing is multi-threading. The CPU. Do you have a question or question? Okay. Oh, you're just stretching? Okay. Another thing is that CPUs have multiple threads, which means the same, like different programs can run at the same time on a CPU. So one optimization you might be able to do is moving the computation part of this image processing to the background thread. So you run it at the same time as your other code. So you're not waiting on this to continue like doing other operations, right, on your robot. So your robot wants to keep moving. You want to keep making decisions. You don't want to really like have this hold up everything that you're doing afterwards. So you can kind of like create a new thread and perform all the like the heavy calculations on the background thread, and that way you can like kind of run these at the same time, and it'll basically speed it up a little bit, and yeah, it won't impact the main running of the program very much. Any questions about this part? Okay. So for example, last year we had to detect the position of an object over one of the markers. I kind of already went over this a little bit, but what we did, instead of detecting the object itself, it was easier to look at where the markers were, because we knew that was going to be the same every time. They're always going to be blue at that angle, at that shape, whatever, right? And that many pixels. So instead, we just basically divided the image up into sections for each blue tape marker, and we counted the number of blue pixels within that section. And this really helped because not only were we able to detect which one was covered, this works with any object covering it that's not blue, obviously, because blue pixels kind of messes it up. But this really worked well because we were able to cover the tape markers with any type of object we wanted, whether it be like our alliance partner, which is like the other team you're playing with. If they wanted to use their object on our side as well, we could allow that because we can still detect where the tape markers are. So this was actually really nice for us to use. And like again, another example of how you can like detect the object without detecting the object by itself. In this case, we're just counting, right? We're not actually detecting the tape marker. We're just counting to see which one's covered and which one's not. I believe there's another example. Yeah. So this is more of what we did this year to find junctions and cones, especially cone stacks during autonomous, because a lot of the time with our previous design of our arm, the arm would sometimes be off, or maybe the cone stack was off, or maybe the driving was off. There's a lot of factors that go into where things are and like how accurate your program can be. So as you can see, this really works well with different types of things. This is a different color, but we're still able to apply a different hue range filter to be able to filter out everything around it. And you can see there's like a nice border around where the junction originally was, and this is really easy for you to work with, and it's kind of obvious where the pole is for the computer now. And the same thing with the cone, although it's a little bit worse. Like you can see there's like a little bit of like noise here where there's like a reflection of the light around it, and also down here where there's a lot of shadow because it's between the cones, but it's still mostly good, which is enough for us to work with and enough for us to aim our arm at or just our driving at or whatever. So yeah, that's just really helpful for us, and we can detect different types of shapes, stuff like that. Usually lines work. For example, in the pole, we can like detect a line of pixels instead of the shape. It's faster and it works. Same thing with a cone, we can still detect a line and find where the middle point is. And yeah, that just works really well. So any questions about the examples or like possible like extensions to this you can use in different circumstances, anything? Okay. If we don't have any questions, I guess we can move on to other. Oh, you have a question? Oh yeah. Okay. So I'm gonna send my PowerPoint. Isha has my PowerPoint right now. So Isha, are we gonna have like a follow-up email to everyone after? Okay. Yeah. Okay. So in that email, we're probably gonna include a link to the PowerPoint, and then everyone can like read back and click on the links that I provided and stuff like that. So there's a much easier way. The only problem with this is really powerful. It's really accurate. It's really nice, but it's hard to get started with because you have to code everything by yourself, or at least most of the stuff. All of the logic comes from the programmer. So if you're just looking to get started with a little bit of this type of stuff, not TensorFlow again, but still you can analyze like the colors and stuff. OpenCV is a really good like alternative. That's like a library already provided. Again, here's a link. You guys can click it when the link is sent out to everyone. It's like easy OpenCV, and it's in terms of like detecting, part of it is like the same thing as I just described, except there's like limited features, although the features are very varied and they have like a lot of different stuff you're able to do. You can like draw on images, you can display images on the phones. It's really powerful, but like again, like I said, I really like doing like coding it myself because then I can change it however I like, right? But this is a really, really good version, and it works for like 99% of whatever you want to do. It's just, yeah, it's a really good thing to start with as well. So this is very widely used by FTC teams, and there's definitely a lot of documentation online, examples. This GitHub repository has a lot of examples on its own, and you're definitely going to be able to find a lot of videos or like a lot of articles on how you can use this for your circumstance or your scenarios. And yeah, any questions on OpenCV? Okay, if not, that's the end of my presentation. So yeah, thank you for coming to the breakout room.